All right, so just a really brief summary of what's going on in your circulation. You have your heart being this main pump, pushes blood out. Any vessel that's taking blood out of the heart is called an artery. Where's my keyboard? Here's my keyboard. So arteries carry blood away from the heart. In general, if we have a blood vessel that's carrying blood that's rich with oxygen, blood that's bound to oxygen turns bright red. We'll talk about that in lots of detail later, but we use red for meaning oxygen rich. So this thing here that's leaving the heart, this is an artery carrying oxygenated blood. This main artery is called the aorta. We'll talk about more. It's leaving the left ventricle here. It's going to just go into capillary beds that are then going to kind of go all over your body. You've got literally 100,000 kilometers, like 60,000 miles of blood vessels get into every little bit. Oh, let me turn off my video here. Go into every little bit of your body, distributing oxygen, and then picking up carbon dioxide. After the blood has delivered its oxygen, it turns darker. So when we draw things that are blue, we're talking about blood vessels that are carrying mainly deoxygenated blood. Again, we're going to talk about that in so much more detail. It's going to come back. It's going to come in to the other side of the heart here. This right side. The right side of the heart is taking this blood that's deoxygenated, returning, and then it's going to go off. Where does it need to go after it comes back to the heart?
Lungs.
It's going to go to the lungs. So we're going to have capillary beds that go into the lungs. In the lungs, you pick up more oxygen. You're oxygenated again, and you're coming back into the heart. Here, where we have blood returning to the heart, this is basically the vena cava here. Anything that returns to the heart is called a vein. Veins return to heart. So one important thing to remember here is this is a vein, it's blue returning to the heart. This thing here, where we have our deoxygenated blood leaving the heart to go to the lungs, is that an artery or a vein?
Artery.
It's an artery. So arteries don't have to be red. Arteries can be blue if you're on the side with the lungs. The side with the lungs, we call the pulmonary circuit. The side where you're delivering blood to the body is called the systemic circuit. So this is kind of, and this gets more complicated. We're going to look at in lecture in more detail. But for our class right now, you are sending blood out to the body. It's coming back. So every heartbeat, and remember the heart beats. It's not like just a pump that keeps going. It boom, 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 boom. That's going to be important. When the heart is squeezing and pushing blood out, that's called systole. Systole is the heart contracting. Maybe I should do that. After the heart contracts, it kind of relaxes and refills. That is going to be called diastole. So that's going to be important too when we start talking about, again, this is, can I move that? Yeah. I'm going to put this kind of off on the side so you don't think it has to do with either. So this has to do with the heart. We're talking about the heart. When the heart is contracting, pushing blood out, it's systole. When it's then relaxing and refilling for the next heartbeat, that's diastole. So when we're talking about the blood pressure going through the system, it's going up and down, right? When the heart is in systole, there's a lot more pressure because as this is pushing and the ventricles are squeezing, the blood pressure goes up. When the ventricles are relaxed and refilling, the blood pressure is not going to be so high because the ventricles aren't squeezing and pushing. It turns out your blood pressure does not go all the way down to 0 when you're in diastole, which might not make sense at first, right? When you're in diastole, your heart is completely relaxed. It's not pushing at all. Does anybody know what keeps the blood pressure going even though the heart is not pushing when we're in diastole? Any ideas?
The muscles in the arteries?
So that's a good guess. The muscles in the arteries we're gonna see are purely about changing the diameter. They don't actually generate any kind of propulsion, but what it's going to be is elastic tissue in the arteries. These big arteries like the aorta, when you are in systole, they get all kind of expanded. So under the high pressure of systole, this aorta is going to kind of balloon out, kind of like a rubber tube that's all stretched out. And when the ventricle then relaxes, there's a little valve here that makes sure the blood can't go back up. So then as this elastic artery starts compressing back, that is going to be keeping the blood flowing along. So I don't know if people used to play with water weenies. When I was a kid, we had these things called water weenies. They're kind of like rubber tubing that you'd put on a hose and they'd fill up with water. And now they've got this big sausage with rubber sausage that's all stretched out, filled with water. And then you go find your friend and you let go of the end and you go soak them with water. So basically during systole, these big elastic arteries get all expanded, filled with blood. During diastole, even though the heart is no longer pushing, that elasticity of this aorta, or we'll see later on the pulmonary trunk on the other side, continue to squeeze and push the blood out to the body. So we're going to see the blood pressure highest during systole when the heart is actually contracting and drop down, but it doesn't go to 0 during diastole because the elasticity of the arteries are going to keep the blood pressure up. One thing that is part of this that's going to come up when we look at our data, I should mention here. I'm going to go to a new picture here. If I think about, let's make it hard. Here's, let's say, the heart. And here I'm sending blood out to the body. There's this little one-way valve. This is called the Semilunar Valve. We'll talk about in more detail later. So even when the heart is relaxed, there is still the diastolic pressure on the other side here, pushing back. It's propelling the blood this way, but it's also pushing back against this valve. So when we begin systole, when we start actually squeezing and contracting the heart, at the beginning, even though the ventricles are starting to squeeze, they're not actually pushing blood out into the body. Again, we're going to look at this in more detail. It's called isovolumetric contraction. It's squeezing, But until you actually get stronger than the diastolic pressure on the other side of the valve, you actually aren't going to be pushing blood out into the body. So we're going to actually see this in our data in a little while. Like when you want to increase blood flow into the body, you want to increase like systolic pressure, because higher pressure means there's more flow everywhere. But higher diastolic pressure is actually going to mean your heart squeezing harder with nothing happening, because diastolic pressure is what the heart has to overcome to actually eject the blood out into the body. And if I'm going through this fast, we're going to look at this all in more detail in lecture, but I just kind of want to put that out there right now. The last piece that we need to talk about is which side here, the systemic circuit or the pulmonary circuit, do you think is gonna need more, is gonna have more blood vessels? You're gonna need more blood vessels to reach every single part of your body, or to go to the lungs and come back?
Systemic?
Yeah.
Systemic's gonna have way, way, way more, hundreds of thousands of miles of blood vessels compared to the pulmonary circuit. So it turns out you need a lot more pressure to keep that flow going. And when you have so many more miles of vessels, you have much more resistance. You need more pressure to keep the flow going. So the blood pressure on the systemic side is way higher. It's like 4 or 5 times higher than what you find on the pulmonary side. So that is actually going to be important. Pulmonary circuit, much lower pressure. When we talk about blood pressure, oh, their blood pressure is 120/80. We are not talking about pulmonary circuit. We're talking about systemic circuit. We are measuring, looking at systemic arteries. We're talking about that 120/80 is the systemic circuit. You can't really measure the pulmonary circuit. So when we're talking about blood pressure, we're talking about blood pressure first in the arteries, and we're talking about arteries on the systemic side. On the pulmonary, on the veins, by the time you make it through all this and get back into return, the blood pressure is really low. In fact, we're going to talk about all sorts of special tricks your body has to keep the blood flowing in the veins, because by the time you get back to the vena cava here, you're basically like at 0 millimeters of mercury. There's almost no pressure left. So when we talk about blood pressure that we're talking about here, one is we're talking about arterial, we're talking about systemic. Again, in the veins, you have very low pressure. Again, we're going to talk about that in way more detail. On the pulmonary side, also much lower pressure because you don't have as many vessels, so there's less resistance. You don't need as much pressure. Units, let's talk about units. Measured in millimeters of mercury. Hg is mercury. I wish I don't have it here. Old blood pressure cups literally had a thing filled with mercury, and then they would have a tube that was connected to the blood pressure cuff that would connect up into there, and whatever pressure was pushing, you could see how high the mercury would go in millimeters. That was the measurement. If I say somebody has 120 millimeters mercury of pressure, it literally means that that much pressure will push a column of mercury up 120 millimeters. It's a very literal kind of unit. If I said 80 millimeters of mercury, that means that's enough pressure to lift a column of mercury up and keep it up 80 millimeters of mercury with respect to gravity. So whenever we talk about the pressure units, we're always talking about millimeters of mercury, and it's literally how much that much pressure will keep a column of mercury that many millimeters up above gravity, or what it wants to fall down to. Okay. Any questions? I kind of blown through this quick, but this is kind of the core circuits. So then, if we look at pressure, it's going to be arterial pressure, systemic arterial pressure. Let's have this be like, I don't know, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. So this is like 140, this is 120, this is 100, this is 80, 60, 40, 20. So this is pressure on this axis. On this axis, I'm going to kind of try to do, this is systole, the heart is actually squeezing. Then we're relaxing, we're in diastole. Then the heart squeezes again. Then diastole. Then the heart squeezes again, that's systole. When the heart is squeezing in systole, that's when you have the highest pressures in the arteries. So let's say this is around here. During diastole, the heart is not pushing. The pressure is going to drop, but it doesn't drop to 0 because of the elasticity of those large arteries, like I was saying. So it starts dropping, but it doesn't drop to 0. It stays at some level. And then systole again, it's going to push back up. But then diastole, it's going to drop back down. But systole, it's going to go back up. So your blood pressure is constantly going up during systole, dropping back in diastole, up again, systole, back down. Whatever pressure that we find it gets up to during systole, that's the systolic pressure. And then when you look at how far did it drop during diastole, that's just going to be the diastolic blood pressure. So you're constantly going up and down between systolic and diastolic blood pressure. The distance, there's a few calculations you can make in here that you actually need to know. If I look at the distance between these two, that is going to be called my pulse pressure. So this distance right here, like this is what you feel. If you're feeling your pulse, it's going up and down and up and down. So if I can add another thing, pulse pressure is just the systolic minus the you silly goose. Systolic minus diastolic. So when you talk about pulse pressure, it's just this difference in there. What else? When you write down somebody's blood pressure, you usually write it as systolic over diastolic. So for this person here, if they're systolic, it's going up about 120, diastolic comes down to 80. We would say that this person here has a blood pressure of like 120 over 80 millimeters of mercury. So whenever you see the blood pressure, it's usually written as two numbers, systolic over diastolic, and systolic over diastolic. The last thing I'll say, like sometimes, like in research, for instance, you'll want to just use one number. It's kind of awkward. You want to have some graph of blood pressure versus whatever. So I want to have an average. Well, okay, I have two numbers for blood pressure, but what's the average blood pressure? The number we use for the average blood pressure is something we call the mean arterial pressure, the MAP. And the mean arterial blood pressure, you might think, oh, it's just like an average of these two, but it's not, because the pressure spends more time down closer to the diastolic than the systolic. So it's actually it's 1/3 of the way up. So it's the mean arterial pressure is going to be whatever this diastolic is plus 1/3 of this distance here. So it's going to be 1/3 of the systolic minus diastolic, which we also said is known as pulse pressure. So you should know mean arterial pressure. Like in your lab that you're going to be doing in just a second, you are going to be using fake data to get somebody's blood pressure, but then you should be able to, once you get the systolic and diastolic, you should be able to calculate their pulse pressure, which is just the difference between those two. You should be able to calculate their MAP, their mean arterial pressure, by this equation here. So any questions? This is kind of all the background you need. Any questions? It's like a lot I've kind of just dumped on you there. All right. So if you wanted to actually measure somebody's blood pressure, you could go invasively stick some little sensor in their artery and measure it, but that'd be pretty bad. You know, we want to have some way to get your blood pressure without sticking a sensor inside your actual blood vessel. So what we're going to talk about now is the classic way to indirectly measure somebody's blood pressure. And normally we would actually be doing this physically in class. We actually, more recently, we bought really nice stethoscopes and blood pressure cuffs and all that, but we are going to talk about it and simulate it. So this has a big wonky name, the auscultatory method for the indirect assessment of blood pressure. Mouthful. It's going to use a stethoscope, which you've probably all know. It's basically a thing that you put in your ears and you can listen with. And then it's also going to use what's called a Stigma Manometer, which you probably know more, which is basically blood pressure cuff. So first we should talk about this weird word. What is auscultate? It's something to do with stethoscopes. What do you do with a stethoscope? You
Listen.
You listen. Listen. So auscultate, this means just listening. We're going to be listening using a stethoscope. The blood pressure cuff is a way that we're going to be able to take somebody's arm. Here's their arm. We're going to put the blood pressure cuff over here. There's two things. One is it's going to have a little bulb that you can use to pump it. Which basically pumps air in. And then it's going to have a little gauge that tells you millimeters of mercury. 80, 100, 120. Basically, this gauge tells you how much pressure is this cuff pushing on. So that's the Stigma Manometer. It's basically this way that you can squeeze the arm with pressure. Using the pump, you can pump it up as much as you want. There's also a little valve that you can release the pressure with. There's also a little release valve. So you can pump it up, you can release the air, and then you can read what is the actual pressure that it's pushing. The artery that we're going to care about is going through the arm. It's called the Brachial Artery. It's coming down from off your subclavian. So that's we've almost got it all. So again, brachial artery coming down. Again, it's underneath here. And the stethoscope is going to be placed sitting right on top of where the brachial artery is. So what you're going to be listening to is, what does the brachial artery sound like? So this is the setup. You have a way to listen to the brachial artery. You have a way to squeeze the brachial artery or release the pressure on the brachial artery. And you can read what pressure you are squeezing with at any moment. And so using all these different parts, we are going to be able to figure out what their blood pressure is. So in the beginning, if cuff, let me use a typer tool. If cuff is deflated, no pressure, what does the sound of the brachial artery sound like? Oh, that's wonky. So what do you think? If you have no pressure in the cuff, so there's no compression on the brachial artery, and you've got the stethoscope, you're listening, what do you think you're going to hear? Anybody have an idea?
Like your pulse?
Right, so if you had your fingers there, you would totally feel your pulse. But it turns out you don't hear anything. It's silent. And it's a little non-intuitive, but it's silent because we have what's called laminar flow, smooth flow. As long as the blood is flowing smoothly, it doesn't really make much noise. I can kind of demonstrate, like if air is flow. If I have air flowing in and out of my mouth, you don't really hear it. But if I kind of constrict it and it's all turbulent, but if I If my mouth is wide open, I have air coming in, you don't hear it. That's that smooth flow. If the vessel is constricted and you get that turbulent flow, then you actually hear sounds. But if the vessel is not being constricted, then it actually is silent. So that's going to be the key to this whole process, is that when you have no pressure, no constriction on the artery, it's silent. It's called laminar flow. However, if cuff is compressing artery, constricting the flow, what do we hear? This is less wonky. What do we hear?
You hear the beats.
So kind of going back to what I was just talking about with like my pursing my lips, you're going to hear sound due to turbulent flow. So you're going to hear and they have a special name. They're called the Korotkov sounds, or sounds of Korotkov, named after the dude, Korotkov. You should know that word. So if you are compressing the artery, assuming that blood is still kind of moving through it, you're going to hear this as the blood is making it through, but it's turbulent. So this is at the core. These are the kind of the concepts you need to understand, and then we can actually talk about the actual process. Are there any questions here? This idea, if the cuff is deflated, there's no pressure, you don't hear anything. If the cuff is compressing the artery and constricting the flow, we actually hear that sound due to turbulent flow. I mean, the other option I can put here, if cuff is inflated above systolic pressure, which is the highest pressure that the blood has, what do we hear?
Nothing.
Yeah, why?
Because you haven't hit your systolic pressure. You're silent.
But why does that, hold on a second, I need to put on a charger here so I don't lose you all. But why do we not hear anything? Again, go back to like this picture here. I really want you to think about it in terms of, if I have the pressure in the cuff higher than the systolic pressure of the blood coming in, why am I not going to hear anything?
It's compressing the artery.
I mean, it was compressing the artery when we heard the sounds of Korotkov as well.
Will blood flow be cut off?
Yeah, the blood flow is totally blocked. So if the pressure in the cuff is stronger than the systolic pressure, then even though the blood is trying to push underneath, it can't make it. So nothing comes out the other side. It's silent because there's no blood flow at all. As the pressure in the cuff starts going down, in fact, let me erase some stuff here so I can actually just kind of just talk about this now. So when we're going to do this, the first thing you're going to do is, pump cuff up above systolic. You know, what does that mean? Most people's systolic blood pressure is not going to be above 120, 130, 140. So you don't want to pump it higher than you need to. I saw some stuff on the web where they're like pumping it up to 250 or so. That's ridiculous. That's going to hurt. So you have to just pump it up above systolic. How do you know if you're above systolic? If you pumped it up and you hear and it's silent, then you know you're above systolic. If you pumped it up to 160 and you realize, boop, boop, you're hearing sounds of Korsakoff, then you got to pump it higher. But you just have to pump it up, go up to something that you're pretty sure is above systolic, somewhere around 160, 180. And that's where we're going to start. And it's going to be silent because you have completely blocked the blood flow. You know, then you are going to start let air out of the cuff. I talked about there being that little release valve. You know, you release kind of slowly, like maybe like 2 millimeters of mercury per second.
I actually
Okay.
have one with me. It's like this.
Yeah, so that's the little pump you used to pump it up. Do you see that little, on Megan's image, there's that little valve, that little round thing she's touching with her index finger? Yeah, thank you for showing that. That is the release valve. You know, and depending on how tightly it's screwed in, it'll let the air out faster or slower. So you unscrew it just to the amount where you can see the pressure gauge going down somewhere around 2 millimeters of mercury a second. If it goes too fast, you're going to miss everything. Too slow, you're going to prolong the suffering, right? It's a tourniquet. Your subject does not have any blood flow to their arm during this. So you do not want to make it last longer than it needs to, because that's really bad bedside manner. So you let the air out. As the air bleeds out, you listen. At some point, what's going to happen as the blood pressure cuff has a pressure lower than your systolic?
You're going to stop hearing it?
You're going to say it again?
Will you stop hearing it again?
You'll start hearing it. Right? So right now it's
Oh,
silent.
yeah. Sorry.
So it's silent. As soon as the blood can finally squish underneath, that means that you are below systolic. So when you start hearing those sounds of Korsakoff, right? When you hear the sounds, those little, then you know that the blood is actually managing to squeeze past the cuff, which means it has more pressure than the cuff has. But it's still compressed, which is why it's turbulent flow and you're hearing all these sounds. So does that all make sense? Yeah.
Mm-hmm.
So then you keep letting the blood flow, the air flow out. We get to 4. You keep letting the air out. What's going to happen once the pressure in the cuff is below your diastolic?
I'll stop hearing. Silent again.
Yeah, you'll stop hearing it because there is no more blood flow, no more compression, so no more turbulent flow. You know, when you stop hearing the sounds, you're basically back to laminar flow. You note this as the diastolic pressure. So this is the whole deal. Are there any questions? Everything else for the lab today is going to be kind of using this to explore different aspects of the cardiovascular system. But the first part of this lab is you need to understand how to measure blood pressure. So this, again, the two things we're going to do for this first part here is you need to understand the technique. And two, why it works. The theory. So as you are going through the different things you're about to do, you want to keep track of both how do you do it, how are you actually taking the blood pressure, but then also remember, like, how come it's silent? And it's silent for different reasons. When you first pump up the cuff, it's silent because there's no blood flow. When you're down below diastolic, it's silent, but it's total blood flow, but it's smooth blood flow. So make sure you think about the theory as you're going, as well as the just actual technique that you're using. Other things, again, if we were doing this for real, once you're down below the diastolic, you keep going down a little lower to make sure that it really was it. But then you just like release all the pressures, and so they don't have to feel it anymore. So are there any questions about this process right now? Okay, so then what we're going to do is this. I'm going to show you, if we go, I'm going to share screen. Thank you. Okay, so back to modules. In the modules, at the bottom of the modules, there is a brand new module called Blood Pressure Lab. So background information videos, you can check these out. Back to modules. After you feel pretty good, you know what you're doing, this little simulation, you click on it. You have to use Flash. And it has different stuff going on. There's an introduction, there's concepts, positioning, procedure, chord, cough, sound. And then what I want you to do is go into the simulation area. And under the simulation area, you actually click simulation 1. There's simulation 2, there's simulation 3. And in a simulation, you actually pump up the thing. It's kind of silly, but it's what we got. And then you can start letting the air out. And as the air goes out, you can listen. And as you listen, you're going to have to notice, like, when do you start hearing the chord cough sounds? Like in this one, with blah, 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 looby dooby doo. It's like, whoop, I hear. So you're going to be noting, like, when did it start? Let's stop this. So you get that idea. So I want you to do those 3 simulations, and you're going to actually have a little quiz that is going to ask you, like, what did you get for those 3 different simulations? So kind of write down on a piece of paper your answers so you can remember what they were when you take this little quiz on here. The quiz also has some basic questions about what do the sounds mean and things like that. So it's 11 o'clock right now. So what I would like you to do is, like, for the next half an hour, just go kind of review what the idea of taking blood pressure means. Do that little practice taking blood pressure simulation, and do this little quiz. It's just a few questions. It should only take you like a few minutes. So do whatever you need to figure out how to do it. Make sure you record your simulation answers, because there'll be questions like a multiple choice on the Canvas quiz that asks you what you got in those 3 quizzes. 3 simulations just to kind of make sure you've done it and you kind of got it. And then we will reconvene at 11:40. The next thing we're going to do now is actually use blood pressure as a tool, basically as like a dependent variable, right? We're going to be using blood pressure to see the whole process of learning how to take blood pressure is so we can now like explore things that affect blood pressure. And so let me get into that. I am going to share whiteboard. So basically we're going to be looking at blood pressure, as well as pulse rate, which is, and again, when we get into all this in lecture, you're going to see, heart rate is going to be connected to all sorts of things going on with all these things are interrelated. So for right now, that we're going to be looking at pulse rate and blood pressure as these 2 variables that we'll keep looking at in different situations. Blood pressure, you would have measured using your, I have this extra camera on that looks silly here. Blood pressure, you're going to measure using the technique you just learned. And in reality, hopefully at some point sooner than later, if you haven't actually done it, you'll do it for real, because it's not exactly like clicking on a screen. There's more subtlety to it, but you do get the basic idea. Pulse rate, how do you measure the pulse rate? What do you think?
Systolic minus diastolic.
So you're gonna have to, you put your fingers on a major artery. You can measure pulses in different places. Obviously,
Your radial.
the radial artery is a really common one. Although another common place is on your carotid artery. In fact, one of the exercises we're going to do today, you're going to have one hand in ice water, one hand is up in a cuff, and there are no arms or wrists to take a pulse from. So you have to take the pulse from the neck, from the carotid artery. But there's lots of other places to take the pulse from. And clinically, actually, they take pulses all over the body because it can give you a sense of how strong the blood flow is to different regions. So those are going to be the 2 dependent variables in all our things. We're going to look at how is blood pressure and pulse rate affected by a variety of things. And we're going to look at how are they affected by exercise. In exercise, you're using your muscles. We're going to talk all about this in more detail, but when you're at rest, maybe only 10% of the capillary beds into your muscles are open. Like right now, when you're just sitting watching a computer screen, you don't need a lot of, metabolic support to your muscles. So 90% of the capillary beds in your muscles are just kind of closed off. When you start doing some exercise, you're going to really increase the amount of blood coming in here. When you are increasing exercise and things, you can like increase the flow coming out of your heart like 4 to 5 times or even more. And to increase that flow, you are going to actually need to increase the blood pressure. We're going to talk about all of these relationships. So it's not going to be that surprising to see that. We're going to look at pain. To look at pain, we have this thing called the cold pressor test. You put your hand in ice water, it really hurts, but it won't cause tissue damage. It's a classic way. If you read a lot of different studies looking at pain as an independent variable, lots of studies are out there that use this cold pressor test because it's a way, it hurts really bad, but it's safe. So you'll see we actually had Becky volunteered to be the one on the video to put her hand in the ice bath. One of the other physiology teachers. And then 3, nicotine. And so we're looking at kind of acute effects of nicotine. There are more long-term effects that it can cause, you know, in terms of like the cancer or this or that. But we're looking just at acute effects. Like if you look at her and you're getting the nicotine into your bloodstream, what are the immediate effects while the nicotine rises in your bloodstream on your blood pressure and your heart rate? And we'll talk about what we see and why that makes sense. I will say, just to start, nicotine is a vasoconstrictor. Again, what you can probably kind of guess what that means. What does vasoconstriction mean?
Constriction of the vein.
Blood vessels.
It's a constriction of the blood vessels. It's going to take a blood vessel. Like here's your blood vessel. Vasoconstriction is make it smaller. We're going to look at all the math and kind of fluid flow around this in a little while in lecture. But basically, if you have a certain amount of flow in your blood vessel, flow would just be like liters per minute of blood going through. If you constrict a vessel and you want to have that same amount of flow coming out, you need to have more pressure to keep it going through faster to get. So in general, we're going to see this in our lecture in much more detail later. But basically, when you constrict a vessel, you increase the resistance, which means you need to increase the pressure to keep the flow going. So that's kind of a teaser. You kind of need it to think about our lab today, that if you constrict a vessel, you're going to increase the resistance to flow, which means that the pressure is going to need to go up to keep the blood moving at the same amount of flow. So that being said, there are going to be some kind of a challenge, whether it's exercise. We're going to use this thing called the Harvard Step Test. Or the challenge might be pain, which is going to be that cold pressor test. Or it might be nicotine and use a Nat Sherman or something. So there's 3 different parts to this lab. Each part is going to have its own little section in your write-up. You'll talk about, you know, for the objective is going to be, you know, how does exercise affect the person's heart rate, pulse rate, and blood pressure. Each of them will have their own kind of methods, which are in your lab notebook. There is a data Excel spreadsheet that is up on Canvas. There are little, I'll kind of show you, guide you through it in a few moments, but basically each of these different sections has its own little tabs where you can look at the raw data for exercise or pain or nicotine, as well as graphs that we have pre-made for both exercise, pain, and nicotine. So when you're doing your write-up, kind of keep these kind of sequestered, you know, kind of write up about, okay, here is exercise versus blood pressure. Here's what we did. Here's the data. Here's my interpretation. Here is pain versus blood pressure. And here is what we did. And here is what it means. and here's nicotine, and here's what we did, and here's the data, and here's what it means. In each of these, you're going to always start by taking a baseline. Blood pressure and pulse rate. So that way you're going to be able to see how it changes, right? Because everybody is 130 over 90 high or low. It's like, who knows? It depends what their resting heart rate, right? The resting blood pressure is. So you'll start in all of these for the subject. We always take their resting blood pressure and their resting pulse rate. I should say one of the things you don't get to experience in this virtual world is this what we call white coat hypertension. Usually I would actually take a student and have them in front of the class, and we'd, you know, wrap their arm up and pump up the cuff and demonstrate this whole process in front of the class. And often they have really high blood pressures, you know, and it's not because they actually have hypertension. It's because they're kind of nervous and mortified to be like in front of the class and all, you know. A lot of times when people take a blood pressure in a clinical setting, it's actually more elevated than the person's actual blood pressure, because people get nervous when they're have a doctor taking their blood pressure. So yeah, so the term they often use is white coat, you know, hypertension. White coat meaning it's a doc. There's a doctor, somebody in a white coat is there taking your, you know, and doctors just make people nervous. And it's like, I hope I don't have high blood pressure. Oh, I'm getting stressed. And they actually have a higher blood pressure than they actually would have had if they were relaxed and you're getting more of a realistic readout. So that's just one of the things that can make getting an accurate blood pressure reading tricky, is people sometimes get nervous when you know they're taking your blood pressure. But anyway, back to this. You'll take a baseline reading, and then you take three readings, like after 1 minute, after 2 minutes, after 3 minutes. So for the exercise, you're going to have their baseline, then they're going to exercise. Then you start a timer, 1 minute post-exercise. What was their blood pressure and heart rate? 2 minutes, 3 minutes. For the pain, you stick their hand in ice water. So here the thing starts immediately. So you start a timer, they're in pain. What is their blood pressure and heart rate after 1 minute in pain, 2 minutes in pain, 3 minutes in pain? Nicotine, you have them smoke a cigarette, get the nicotine in their body, start a timer. What is their blood pressure 1 minute, 2 minutes, 3 minutes after they smoke their cigarette? I will now just kind of guide you through some of these videos that we made. So I'm going to now share. You find it. Here it is. Let me go into share screen. Okay, so we're going to go back into our module here. And we're going to go into doing the blood pressure lab. So we did it. I took it into Premiere, edited it, tried to make it pretty. You'll get some sense of what you would have been doing. This first one here is just 2 minutes. This is Becky just kind of showing the equipment and also talking a little bit about using a stethoscope. When you use a stethoscope, it's important that the piece of the earpieces actually face in towards, like they have to face backwards towards you, because your ear canals kind of, actually it goes the other way. If you put them in your ears just kind of the wrong way, they actually just hit. So they have to kind of go be going towards you, so they actually go into your ear canal so you hear well. She'll talk about it right now. So here we go. This is Becky introducing the basic equipment for the lab.
So this is all the equipment that we're using for our blood pressure lab.
Yeah, the alcohol is just so you can get growtiness off of the stethoscope before you put it in your ear.
Stethoscope, you want to make sure that the ear pieces of the stethoscope are angled where they're angled in a forward direction, because when you put them in your ear, the ear canal will follow that forward direction. So then on this end of the stethoscope, it has two ends, but only one is used at any given time, and it twists. So whatever end you're using, you want to make sure that there's a dark hole where the sound waves are going to come into that side, and the other side should not have a dark hole where it's covered.
You can just give a little
forcing
tap
the
and
sound
you can
waves to
tell.
come into one side.
And for us, since we're using adults, we'll use the larger bell. The smaller bell would be for pediatric subjects.
And you tap it just to make sure there's a really good sound. So
Sure that the stethoscope is over my brachial artery, which is the artery we'll be auscultating, and the Stigma Manometer cuff, this blood pressure bladder, is going to be able to pump up to pressure, which we can read here, and see what your person hears through the stethoscope, the sounds of coric cough that will start appearing as the artery starts getting compressed.
All right, so that is the kind of introduction. I mean, another thing that we would have done in lab is have you all spend some time feeling your, let me get out of this. Another thing we would have you do is find your actual brachial artery, because that's important too. You got to know where the brachial artery is, kind of medial, right above your elbow. If you dig in, you can actually feel it kind of thumping in there. Like I can feel my brachial artery pumping right now. All right, so now 3 minutes and 36 seconds, you are going to see the Harvard step test. This is something that was originally used with these kind of young kids trying to get, figure out their cardiovascular fitness. There are much more, fancy ways to get like maximum, VO2 and things like that. But this does give you some basic crude sense of somebody's fitness using this step test, which I will show you in this video. So, yeah, I don't know why my thing keeps glitching.
All right, we're going to start with an overview of the exercise part of the blood pressure experiment, where you're going to take an initial baseline blood pressure and heart rate for your subject while they're sitting quietly. Then you'll start a timer, and they're going to do the Harvard step test, going up and down on the step for 5 minutes. As soon as they're done with those 5 minutes, you now start a new timer, and you have them sit down, and after 1 minute post-exercise, you'll take their blood pressure and heart rate. At 2 minutes post-exercise, once again, you'll take their blood pressure and heart rate. And at 3 minutes post-exercise, once again, you'll take their exercise and heart rate. After you've got your data, you can calculate their fitness index and continue on. Harvard step test, I'm going to be stepping up and down in a very specific rhythm for 5 minutes. It's 1/2 step, 1/2 second per step. So 1 and 2 and I have to keep up that pace for the entire 5 minutes. So we're gonna she's gonna start me off here. Tell tell me when to go.
Ready, set, go.
You keep going for 5 minutes. My lab partner here is making sure that I'm not starting to slow down. I'm going slow, she's
Keep
going
on
to
there. You can do it.
So be careful not to fall off.
4.5 minutes. Good job. Keep going. Practice your body for physiology.
5 minutes and I'm done. And then I'm done.
Stop.
All right, so now it's done. We start the timer now for as soon as this is done. So it's going there. Now I'm going to get ready to get my blood pressure and pulse taken.
It's okay.
So at 1 minute after the exercise is over, my lab mates are going to be taking their first reading of my blood pressure as well as my pulse rate. For the blood pressure, it's the normal auscultatory method. For pulse rate, you just get it off of my radial artery, or carotid works as well. And you can either count for 20 seconds and multiply times 3, or 30 seconds multiply times 2. Obviously, it's going to take at least 2 people because one person doing blood pressure, one person doing pulse at the same time. In the interest of social distancing right now, we can't quite demonstrate that. And it's 2 minutes post the exercise, we'll take another blood pressure and another pulse rate reading. At 3 minutes post exercise, we'll take our final measurement of blood pressure as well as pulse rate. And that will be the data gathering for the Harvard step test part of the experiment.
Okay. So are there any questions about the basic procedure? It's basically going to get your heart rate going as you do this 5 minutes of intense stepping. And what do you think you might find? What do you expect to find? How do you think that's going to affect your blood pressure and heart rate?
It's going to go up.
It's probably going to go up. So let's take a look at the data. Data. Oh, yeah. Oh, give me 2 seconds here. All right. So if I go into, where did I put the data? Let's go back into modules. There, blood pressure lab data right here. Click on that. I'm gonna open this in Excel. And again, if you take a look here on the bottom, there's exercise with their own graphs. There's ice water with their graphs. We have the nicotine with its graphs. But for right now, we're just going to look at the exercise. Here we have a bunch of subjects. We have their baseline readings when they are, I can go and, yeah, baseline readings before they did the stepping. Then after they did the stepping, what's 1 minute after, 2 minutes after, 3 minutes after. If we look at their heart rate, it's not that shocking. It goes up right after exercise, and then it starts coming back as your body recovers. When we talk about people's level of fitness, like this fitness index that you're going to calculate has to do with how quickly this is coming back down. In general, someone who's more physically fit will not have to increase their cardiovascular activity as much and it will come back to normal quicker than someone who's not as fit. So when we talk about fitness, often that's kind of what we're meaning is like, fitness is how much does your system have to actually increase activity to deal with the extra stress, and how quickly can it come back to resting when you're done with the added stress. So here's the data here. The blood pressure data is a little interesting, a little different. I think we need to talk about. Here is the blood pressure data. And let me maybe zoom in slightly. Oh, too zoomy. Oh my God, hold on. I want to zoom maybe, how about 125? So what do you notice about, did the blood pressure go up during exercise?
Initially.
Initially, I mean, so like the pulse, we see an initial rise and then kind of a recovery back towards baseline. Did both systolic and diastolic kind of do the same basic thing, go up and come back down?
No.
No, there's something really interesting going on here that you need to make sure you pay attention to. Again, if you take a look here, baseline to after exercise has gone way up, and then it's kind of resolving. What does the diastolic do?
Basically stays the same.
Basically stays the same. The diastolic is not going up during this, trying to increase your blood flow. So this is important. Maybe I can use the stamps. Use the star stamp. Important point. Diastolic does not go up, but the systolic does. And there's, it kind of makes sense when you think about it. We talked about how, during, if this was your heart and here was like the blood coming out to your body, and that diastolic is the pressure out here, like in the aorta. And as the ventricle starts squeezing, it has to overcome diastolic before it actually even pushes blood out into your body. So if your diastolic had been going up, that would mean your heart would be squeezing harder than normal, even just to try to push blood out of the ventricle into the aorta. So this part is nice because increased systolic, that means increased flow. You're getting more blood going to all these muscles that have been needing it. Or actually, at this point, it's more about the oxygen debt, recovering from oxygen debt, because this is happening while you're sitting down. You're no longer exercising. So this is actually oxygen debt right here that you're seeing, because your muscles are not actually using this extra blood, delivering extra oxygen while you're measuring this, because your subject is now recovering. But so in your write-up, definitely make sure you look at the heart rate, you look at the blood pressure, make sure you think about the difference between systolic versus diastolic. So any questions about that? All right.
In the lab notebook, so do you want us to do basically the whole procedure like we would if we were an actual lab, or just the write-up and kind of?
No, so you don't actually write. Yeah, so I wrote it in the Canvas thing. I put basically normally where you're going to record the data from your subject and calculate their fitness index. Instead, what's going to happen is you're going to go into the exercise data here and pick one random person. Let me clear this stuff. Whoever it is, maybe subject 8, or pick your lucky number. Let that subject be your subject that you're going to write about, and then use their data to calculate their fitness index. So that's what I would say. And the same thing for the other ones as well. Because you are not supposed to do the step test yourself. You're not supposed to stick your hand in ice water. You're not supposed to smoke a cigarette. You're just supposed to take the data here and pretend one of these people was your people, and then, write them up as they were. And then in your lab write-up, you then add in also all of the group data, which you are then going to integrate into your discussion.
Right. Okay. So yeah, I was just asking, like, for the actual lab notebook, we just kind of do the lab as if we did it and just use that data, how you just explained.
Correct.
Okay. Thank you.
Sure. All right. So the next part then is going to be the ice water. We made a nifty little video for that. So let me show you that one. Where is it? Go back to modules. Doing the blood pressure lab.
All right, here's an overview of the cold pressor test part of our blood pressure experiment. You'll start by taking an initial baseline reading of your subject's blood pressure and heart rate. Again, pulse rate and heart rate are the same here. Immerse your subject's hand in ice water and start your timer right away. Make sure that the water and ice are in equilibrium so we know it's 0 degrees C. After they've been immersed for 1 minute, you will take their blood pressure as well as their pulse rate and record that, keeping their hand in the ice water bath. After 2 minutes, you again take their heart rate and their blood pressure. After 3 minutes, again, you take their blood pressure and heart rate. And at this point, they can now take their hand out of the ice water bath. Then you can continue on with your experiment, calculate their index of response and all.
Okay, so the noxious stimulus and blood pressure relation, I'm going to stick my hand in ice water that has been equilibrated, so a little bit of time for the ice and the water to reach 0 degrees Celsius. And once the timer starts, I'm going to immerse my hand, keep it immersed. My group mates will be taking my blood pressure and pulse for 1 minute after, 2 minutes after, 3 minutes after, while my hand is immersed in ice water the entire time. When we take the pulse, we want to take it from the carotid artery this time because, one, if I took it from my radial artery in the ice, that's not doable. And if I took it from my hand that has the arm that has the blood pressure machine, the Stigma Manometer on it, there's no pulse during the time that the cup's inflated. So the carotid artery is the better artery to take each per minute.
So now we're going to start this experiment. So I've got the timer here. And I'm going to go start as soon as are you ready to put your hand in the ice water?
I think so.
All right, so here we go. Start. She's got her hand in the cold pressor test, ice water, and at 1 minute, we're going to take the first reading. It's genuinely designed to cause pain, but not tissue damage, but it can be quite uncomfortable. Although, all right, so it's almost 3 minutes. At 3 minutes, okay, now it's time to take the final reading, our third reading. We'll have someone with her blood pressure and her pulse, and now we're done. You can get out. All right, you can notice there's that like kind of reflow. It's typical for your hand to get kind of bright red afterwards. Thank you for being such a great participant.
Okay. So this one, let me go, I'm going to share the data again with this one. New share. So even though we do have some graphs of averages, those are not actually interesting. What is interesting for this particular part of the experiment actually is this index of response. So the index of response, you basically take their baseline reading of their systolic and their diastolic pressures, and you look at the maximum change that happened while they were experiencing the pain. And what you find is index of response is really different for different people. So one of the things that I really like about this lab, like it's kind of too bad we can't do it in person, but you can still, this data is real data. This is from real people, real students that have come before you. Some people put their hand in this excruciating ice water and they barely experience much of a change in their blood pressure at all, or sometimes it goes down. Other people do the exact same thing. Right, you know, this person here, they barely moved. This person here, you know, their blood pressure went up by 40 compared to their resting. Some people were low, some people were pretty high, some people were in the middle. There's a huge range. That is kind of like the take-home message, actually, when you're kind of thinking about what this data means. These average, blah, 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 the average data here of, you know, blood pressure versus, you know, that's not really, in general, it goes up. But more what's interesting to me in here is that for some people it goes up a lot, for some people it barely moves. There's this huge variation in what you see in terms of this response. This is something that is really critical to, like, I think, hold on to as you're kind of starting to move more into like the clinical world, is how some of your basic, you know, intuitions, oh, heavy pain is gonna, like, that's gonna jack up their blood pressure. Yeah, for some people it does. For some people it really doesn't at all. In fact, we can look here, this subject 1 here, you know, their pulse rate actually dropped down. It was lower for the whole time they were in ice water. It didn't go up at all. Whereas this person here, this subject, their pulse rate went way up compared to their resting. You know, so both with the pulse rate is really kind of, you know, idiosyncratic. You know, it depends on the particular subject you're looking at. How their blood pressure changes, this index of response is very much dependent on the individual. So I just kind of want you guys to take that away from the data in this lab, that, you know, how, you know, some things that we do in our lab show, oh, there is in general a consistent response that you can, it's kind of predictable. But then there's a lot of things, like something like this, where it's really hard to know exactly, is their blood pressure going to really go up a lot or not? You know, it depends on the person. So again, for this particular lab, in your discussion, I would focus more on the index of response and kind of the variation in how pulse rate went up or down depending on the person to person, rather than really think about the overall averages. These averages we put here just for completeness, but I don't find them nearly as interesting as seeing how variable the data actually is. So are there any questions for that one? All right, so then the last little video is really quick. I will just share it with you guys, and then we're almost done with our lab for today.
All right, part 3 is going to explore the effects of nicotine on your cardiovascular system. It's structured just like the other 2 experiments, and here I'll tell you all about it. All right, for the last part of our blood pressure lab will be a nicotine challenge. This is for educational use only. I don't recommend this as a habit. It's not that good for you. For this one, again, we'll have taken a baseline reading on the blood pressure and the pulse rate, and then the subject will smoke a cigarette, and basically you get the nicotine into the body. And at that point, as soon as you're done with the smoking, the subject is going to sit down and we start the timer again. And it's just like the other parts. 1 minute post challenge. I'll take my blood pressure and my pulse rate, and that'll be the first reading. 2 minutes after I'm done with the cigarette, we'll take blood pressure and pulse rate. And finally, at 3 minutes post smoking, we'll take the blood pressure and the pulse rate, and that will be our data for the nicotine challenge part of the blood pressure lab.
All right, so that is that. And in terms of the data for this, if you look in general, here this, I actually need to make this a little smaller. Let's maybe make it 80%. Back. We have two things going on here. Nicotine is a stimulant. So when you smoke, one thing you can look at is the heart rate. Heart rate definitely goes up with nicotine, and this is what we'd call acute nicotine intoxication. Meaning, like, this is while the drug is in your body, it's increasing your heart rate. It's also increasing your blood pressure. And part of this, again, we talked about, is going to be from this idea of vasoconstriction. I am having trouble here. So it's vasoconstricting. Again, in lecture, we're gonna, next week, we'll talk much more about the effects of vasoconstriction on blood pressure. But for right now, as an introduction, if you constrict a vessel, it's gonna make the blood pressure go up to make sure the flow continues on. So this is not surprising. In terms of the actual long-term negative cardiovascular effects of smoking, it's much more complicated. Nicotine has many other effects in your body, can increase, probabilities of different kinds of, cancers and things like that. But it's more about stimulating like long-term inflammatory processes and things. But what we're looking at here is just like in the short term, nicotine is definitely cranking up your heart rate and cranking up your blood pressure in the moment. So are there any questions about all of this stuff? I'm going to go share again, new share, back to, where is it? Well, no, this is not what I want to be sharing. Stop that. Hold on. Oh, here it is. This is what I want to share. Share screen. So you can, again, you can look at these again if you want, or you just get a kick out of them. Remember again that previous. No, I want to go back to module. Okay. Remember, you've got the blood pressure data is right here. You can get that. Eventually, I want you to submit the write-up as a PDF, but I know that your exam is coming up. So I thought, like, you don't need extra stress of trying to make sure this thing is done by the weekend and study for your exam. So I put the write-up like 2 weeks out. So I would like you to eventually write this up and do your PDF scan and submit it. However, I think it's probably, I want to make sure you have time to think about studying over the weekend. So again, that's why I put it far, a couple of weeks out. The exam that is coming up on Monday, I've gotten more, and it's gonna be through Canvas, including some kind of multiple choicey stuff and some, make sure you've got, I feel bad for people who aren't so good at typing. But, I like to have a lot of short answers as well. So, I'll have to figure out the timing and stuff because I realize that could be an issue for somebody. But it will be something we will do kind of online together. I'm still figuring out some of the details, but I have been figuring out how to kind of create more like kind of test kind of things in this world. So if you have questions about any material over the coming days, or please just email me. I'm happy to answer any questions. I'll have office hours tomorrow. Actually, I don't have office hours today because I have to go to a department meeting in 1 minute, or Zoom into a department meeting in 1 minute. So I could show up if you wanted to talk to me in office hours, send me an email. I can set up a Zoom with you after I'm done with the department meeting a little later today. Or if you have questions about things, you can also email. I'm happy to do that. So are there any comments, questions, or otherwise about all this stuff? Let's see.
So for the test, we just have to log into the Canvas and it'll be like in a module.
I don't know quite yet. If it's a module, it's not going to show up until right before we do it. So I think it's going to be it'll probably be a module in Canvas. Does everybody here have good, solid, unbreakable access to Canvas right now?
Yeah.
Yes.
Yeah.
Okay, so so we'll do it. It'll kind of be available right before we're about to do it, and then you'll do it, and then what is the lab supposed to be? Well, like, hold on one sec. I didn't even think about this. Hold on. So actually, you know what? I'm gonna say because it doesn't matter what day we do things, and because we're not doing a student design lab, I'll send out an email to you all. After the exam day, we'll talk a little bit in lab time, but we're not going to do the EKG lab on that Monday. I'm going to move the EKG lab onto Wednesday. So I'll send an email with an updated schedule there. So don't worry at all about what lab means after the test. That also kind of gives us some wiggle room in case we have to expand how much time it takes and stuff like that as we're trying to work this all out.
Thank you.
Yeah, thank you.
Okay, so
Thank you.
all right, so I hope you all have a good weekend, and and I hope you're making the best of all this. So take care.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.